Hi everyone, good afternoon. My name is Maxim Goryachy. My name is Ermolov, and today we want to share with you. It's even hard to say what we are going to share about. More likely, it's first of all be interesting to those people who would like to know how it all works. In our case, it's a processor, and not only a processor but also the South Bridge. But the point is that, generally speaking, when you are looking at a chip, you can see it as a black box in a way because it has some inputs and outputs, and it's quite difficult sometimes to understand what this chip is capable of, and this whole assignment could be very, very difficult to be able to reconstruct the internal functionality of this microchip by analyzing inputs and output signals. Sometimes it's very difficult, but today we want to show you how, in a very interesting way, you can look inside of a chip without any very expensive equipment like microscopes and analyzers and things like that. And just to give you a different perspective and try to think how it can be implemented on one hand, and secondly, how can you collect information not only directly from your observation but also from all available sources. And I would like to give a disclaimer. All we want to share about may really kill your equipment if you'll try to repeat it. It's at your own. The warning is you can do it at your own risk. We'll give you all the links at the end of our presentation. You can come in, you can ask. Any questions will be welcomed. And another way of disclaimer that this information has been obtained not from some kind of secret knowledge depository. It's all open sources, and we in no way guarantee that our research is an ultimate truth. It's simply a perspective on a problem. It's our own understanding of how it's supposed to be working. And everything we will be describing in all the demos you are going to see, they are based on a vulnerability we have found, Intel SA3086. And if you will see any mistakes, any errors, please do not shy away from writing to us. It will be interesting to discuss it. Now, what a modern architecture, Intel architecture in particular, looks like. In our perspective, this is the way it may be looking. You have the upper part of the tip of the iceberg, where you have public technologies and what students study in universities, commanding system, page and segments, all these extensions, AVX, AES instruction, which enable you to do calculations faster, to be more energy efficient in all your processing and calculations. And also there are certain defensive protection technologies which are described well in terms of the programming model. And sometimes you can only guess how it is implemented in the lower levels, on the level of microchips, but at least the software model is there. Virtualization, PJX, and after that we have the zone of the documentation, although in part some trace hub, which will give you some details about, and ACH, boot card, and then going down at the depth of several meters, you can see MBA and EB and Pro. At least you can find some information in open public sources, in patents, in book, which is written about NE, about MSRs, reboot. You can look in some other sources. It's like a semi-transparent water, where things make sense but not completely. And diving deeper and deeper, where things become darker and blacker, highlighted in italics and bold, are the things we will be covering today in our presentation. And we believe that at the very depth there is a microcode. If you understand how it works and how the format of a microcode, you can change it, you can patch it. on this level. You will be able to study internal processors, internal architecture very well, what's happening inside of it, and things like that. And today we are going to speak about Trace Hub, about the internal buses, about the fixing, and what Intel Visa. It is not really, Intel Visa is not about the payment system, and people who have come here and they think that I'm going to share something about finances, I am sorry, it's not going to be about finances at all. Now, what Visa enables you to do? It's a low-level, uh, logical analyzer, which Intel needs to verify, as we believe, to verify things, to make sure that those chips which are being produced, they comply with specifications, so you can catch all the bugs at the stage of manufacturing. For example, here is a new test chip, and the engineering sample, it does not work, and you can understand why. What are the other capabilities? You can try to restore internal architecture of a bridge, of a processor with this technology. You can also try to attempt of how to work with the cumulative things. Because this demo we are just about to show you, we can tell you that we can route the access to the memory, all those addresses which are physically being put on the addresses bus. If you want to see the Spectre, for instance, you simply have to catch the certain address for those or call for those addresses which nobody should come to you. You are writing your own proof of concept, and almost in an automatic mode, you can try to connect your feedback line, verifying conditions until you can see in the machine the data you are expecting of it. It means that the data has been read, but they should not have been doing that at all. Visa technology, all in all, is quite a complex thing, and in the right bottom corner, it will be our roadmap, our plan for presentation. You will see that at the each stage throughout our presentation, we'll be sharing about each pieces, about the DCI, Trace Hub, and Visa, DCI, and we will also cover the hosting side, what you have to install on your machine for it to be working properly. Now let's basically dive into that. What DCI is all about. Please lift up your hand if you do not know what DCI is. Well then, I'm going to share briefly. Until 2015, to be able to debug your Intel-related processes, you had to have a special motherboard. You had to have a certain adapter. Basically, there was a whole evolution of these debugging tools. You can see them on the picture. And this resulted in a situation that those platforms, which had been consumer platform, you could buy them, let's say, in a retail outlet. With a high degree of probability, they required some modifications. Sometimes they were not even suited to connect a debugger to them. And you, as a result, you couldn't, I don't know, to fix your system. But in 2015, everything has changed. DCI came around, and basically it's a way to speaking about the low-level debugging, to do it via USB. We have already shared about that. The idea is that you need either the this connection fixing cable or a special box, so Intel adapter, through which you can get JTAG simply on the regular platforms, which basically are available in regular retail. DCI enables you to double-check almost on the full scope of your internal devices. It can check against your USB device. You can see how it is functioning, having access to DFX, and basically it's the main technology using which you can debug, you can fix crystals themselves. Couple words about Trace Hub. It's when you need, let's say a device which somehow would be processing not only DCI, because at some point this is not enough. You need a good buffer which is stacking your events or logs. You're developing something and you would like to log something in. And Intel, since the same 2015, if my memory serves me right, from Skylake, they've installed a separate device. It's an internal device into PCH, enabling to want to trace events from BIOS, from ND, from, as far as I remember, also from the port management control. And I would like to give the mic to Mark, and he will give us more details about that. To begin with, I would like to say that today we are speaking about the hardware connecting of the modern chipsets and the SoC chip systems from the Intel company. Speaking about the processors as such, as an integral chip, they also have certain hardware means to get the values of internal signals. However, they are a little bit different, and they could be considered to be a little obsolete because the newer processors on the Cannon Lake architecture, Ice Lake architecture, they are also inheriting this hardware tracking means which came from the system logic. And these hardware routing means are now built into Intel Trace Hub. And they consist of the three main components, Visa itself, and today we're speaking about Visa. They also include a logical analyzer and a logic analyzer and another component system on chip hardware architecture performance. All these components, which can be attributed to the hardware routing, like Maxim said, the Trace Hub is called to solve a problem of accumulating all the diagnostic routing information in the platform in one location. And hardware routing, when you get the values and dynamic of hardware signals, is a part of the Trace Hub. And all these three components are fully managed from the menu of managing registers within the Trace Hub. Trace Hub enables one to get this routing data, to accumulate this data in certain locations, and you can store it into the memory or send them via the DCI. And it also has the dedicated interfaces, for example, such as a PTI, parallel trace board, where any GPU pins can work, and this routing data or tracking data can also be obtained from Trace Hub. That's a little bit more about Trace Hub. Intel implemented some open standard, including on the highest level of the stack, these tracing data are coded in the software operates protocol format, which is a dedicated Trace Hub device. You can get an access to that by different buses or via a PCI bus or JTAG or also SIPAN interface. IOSF, we are going to touch on that a little bit later. Here we have circuit. We've taken it from a manual on Trace Hub. You can find it in public access. Let's put it this way, the reversed version of this manual, because there are references from the Linux kernel, from the source code to this one, so you can find it in public access. And this chart describes the components which are part of the hardware tracing. This controller and dial logic, and here in some documents Visa is pointed as a VIS, in some as a VISA. And the Intel company has developed a quite powerful programming stack to support TraceHub, which includes two big libraries, TraceHub API and Trace Decode Engine. Each of these libraries is supplied with a special utility, configuration utility, an executable file, with which, using the library's functionality, you can do certain actions for which they are designed. Unfortunately, these libraries are basically undocumented. Although they are part of the package Intel System Trace tool, it's a utility quite convenient, has a QE interface written on Java, enabling one to get tracing messages from the BIOS files. And for ME, you can also get messaging, but this utility is based on the TraceHub API on the Trace Decode engine. They are the foundation of all the tracing on the Intel platform. Like I said, unfortunately, we cannot find an open documentation for these libraries, but we were really helped by the fact that for certain versions of these libraries, for the Linux platform, they have binaries and fixing information. You can get all the names of the functions from these libraries and to understand how the things are working. The destination or goal of a TraceHub API is to configure, based on demand, on the user's demand, hardware resources of the TraceHub which may be needed for a certain tracing. And Trace Decode Engine is basically a factory of decoders of the different tracing information collected from different sources. Now we want to demonstrate you a video of tracing of a message from a management engine. It will be done on the example of the tracing utility by Visa. Well, basically, now we are inserting this debugging is a tool which enables you to stop the loading of a platform, not even the CPU, but the platform. We install it, then install the Visa's settings, restore after that the Visa is configured, and we are letting the kernel go. And say, as you can see, the command interface of the utility, this is what it looks like for the tracing purposes. And you can see that the CMSE protocol obtained for mastery 16 by this channel, how many packets and from who? I think 336, this undefined. What was it? But possibly these messages simply were not listed in the registry, and as you can see right now, these are real messages from ME. Some of these messages are like debugging, they're like text messages from within the kernel, while others have this certain rendering. Okay, you have certain ID, and in configuration for this ID, you have the line with the parameters of what it means. Sometimes you can have it both ways. We've shown you this video simply as a demo of the TraceHub operations. It has nothing to do with the hardware signal tracing. Can we get our presentation back, please? And now, briefly about Visa itself. Visa is an abbreviation, stands for Visualization of Internal Signals Architecture. In fact, it's simply a network of the multiplexers, which are called for connecting output signals from the IP units, so logical blocks, to the central multiplexer, and then either to the built-in logical analyzer on a crystal or to an external one. You can actually connect the external analyzers with a Visa, and you do configuration, and you get the same signal from the internal IP blocks if you have the higher precision, higher frequency, and so forth. Within the Visa, there is a certain sub-device enabling to manage all of this network. And each multiplexer in Visa can be one of three types: serium, central level multiplexer, which is the highest level multiplexer, which basically connects with the logical analyzer, and also a lot of interim PLM or multiplexers. And for each IP unit, there is also a set of unit-leveled multiplexers, which get the hardware signals from these units. We believe that one big advantage of VISA is that an engineer working with it, they do not have to know the particular frequency of the signals they would like to obtain the values of these signals, because the VISA operates with native signals within a chip. You simply have to know the frequency identifier, and all the frequency within multiplexers are numbered, and knowing your identifier with the group of output signals operates on, you can basically get values of any signals and to digitize them. And also from within VISA, we know that there is templates generators built in simply to understand whether the network is functioning well. It's not about the logical blocks. And here at this slide, we are showing it a little bit graphically. We can see IP units and different sorts of multiplexers. The register controller, VISA registers controller, is the heart of all the VISA management. It identifies such ranges. It identifies the address space for each multiplexer within MMIO ranges, which is attributes to register controller. And like I said, for each frequency you set a certain identifier, but also for each groups of output signals from IP units, each ULM or unilevel multiplexer also sets the identifier. And these signals, they are clustered to operate more convenient with them, because there are hundreds of thousands. And to make it more convenient to operate them, they are being clustered in groups and lanes. In lanes, about 8 signals in each, and each group is assigned with its own identifier. Also, within the versions, you can find very convenient mechanisms. It's a replay RAM. That is, you can take your whole configuration for a specific hardware tracing. You can record without application, and then with certain inquiry immediately restore this configuration by demand. So you can switch between tracing of different sets of signals from different devices. And now about the file itself, VISA. Our whole research started from the point when we could see the VISA XML file. We really got intrigued by that, by its name, by its abbreviation, which is a very well-known abbreviation, and by its size. It was tens of megabytes of the text XML information. And when we first opened up this file, frankly, we were simply confused by the volume of information. We simply could not understand what is the purpose of all this information. Although we've had quite a big experience, a prior experience of the reverse engineering, we knew how this PCH is built, but seeing all this information from the VISA XML, we could not make out a thing. But time went by, we began to structure this file, and we realized that it consists of the 3 big parts. First is basically a multiplexer description. The next one would be the hardware signals descriptor, and next, registry descriptor. And here in this slide, you can see the 3 sets which are needed to do the hardware tracing of certain signals from the fuse controllers of an internal device. And studying this file from XML, we begin to understand that some information was missing, some information we do see, yet another segment of information is simply not there. We begin to think maybe it's a concise version, maybe some of the part of information is simply been cut out of it. It's not for just regular users. And we were lucky enough to find in different versions of the System Studio, we found two files, Visa XML, for the same platform, for the same stamping, but they were different in size. One of the files were several times bigger than the other. And knowing that in some versions of the System Studio we have the big Visa XML files, we've gone through all the Intel System Studio packets, beginning with the version 13, which we could find it in a public domain, and we are confident that now we have all the versions of the System Studios ever been published by Intel, and we have gone through all the XML files from within the studio, and here on the screen you can see the results of our work. It's a set of all the Visa XML files. We have its size, and for what platform, for what stepping. And if you look into that, it looks like the collection had been assembled in the following way. We've noticed it's quite a phantom file. I mean, Visa XML, sometimes it would show up or disappear at different builds of the System Studio. Yet in some versions, like Mark said, it was less. Yet in other versions, it was bigger. We begin to build this collection. And as you can see, some of the files, they have the same identical size. But as a matter of fact, it's the same file, almost the same file. And since there is a different stepping, you can see changes in some signals. Yeah, the new chip revision inside is different, and these changes are not that many. You can look them up. We compared two files from the same platform but of different sizes, and we could see that in a smaller file there is a lack of description of many signals. They are identical by the describing multiplexer and register, but the number of the groupings of output signals in internal devices were really different. And this was the main difference. We've shown you this in two files. Highlighted in green, what you're seeing is what was lacking in a smaller file. Within the XML Visa file, when describing the registers which are managing Visa register controller, we really looked into such an attribute as standard. The standard for some registers was like a Visa control, yet for others like a Visa lane. And we immediately realized that it's a standard defining layout of a register and its purpose, why this register does exist. Although there was no other public documentation, but by reverse engineering of the Trace Hub API library, we were able to understand this layout and the fields within each of the types of the registry standards. And we came to realization of how to program the Trace Hub's equipment to build a certain Visa network. And now, what the multiplexer, what it looks like from the inside, basically it's a mechanism using which you can, for each outgoing lane, to assign one of the incoming lanes and to set a frequency where these signals will be digitized by a logical analyzer. For several lanes, you can set the same entrance or incoming group. I would like to add from my part, the question is back in, why do we need all of that? Because, okay, we want to trace our signals. Why do we need to build like this superstruction, JTAG extension to reinvent the wheel? Let's take the line out of each signal and somehow we'll be reading that through some kind of a JTAG register. But the point is, like, what we've seen is that very, very often the lines have been cut off. Even to be able to read the memory, you need to use all different hacks. To read all the whole line of an address, you have to use different hacks because they go through one multiplexers, and multiplexers have been invented to make the scheme within PCH easier, because you cannot take out all the lines. There are hundreds and thousands, maybe even millions of lines. And to simplify it, as a matter of fact, Visa probably do not know how to trace just any signal. You mean just any, there are many more signals. But Visa shows you the most important signals. They are taken into the multiplex to cut costs, to decrease number of lines, to decrease complexity of the device. And now very briefly about the logical analyzer itself.
It only has 16 lanes, each for 8 signals. So actually, it can digitize 128 signals at the same time. So this is exactly to select only 128 out of hundreds of thousands. So that's max. Those signals will be digitized by the digital analyzers to get their values at any moment in time. For PCH, the logical analyzer operates at about 400 megahertz. We haven't yet played with the logical analyzer built into model CPUs at Weisley Cannon Lake. I think they will operate at higher rates, but for PCH it's quite enough. At the same time, it can cover up to 128 signals at this frequency. For each input lane, there's a certain arbitration unit that can set the weight for each lane. Basically, it's about the frequency of polling. So some lanes can be higher priority, some lanes can be lower priority. And so at the end of the day, the logical analyzer will code those data in its private format. It's wrap it into the open software trace protocol standard and sent to the trace hub. Well, this one shows you the output of the decoder. The trace information of the logical analyzer using trace decoder engine. We connected it, built a network, and then we'll display all the steps, or show all the steps in a separate slide that you need to take to trace hardware signals. It's not an easy thing to do, by the way, and this slide is to show an example of an inbuilt decoder for logical analyzer in operation. What you can see here, I'm not sure whether you see it or not, but every moment where input lanes are being polled are marked with a timestamp up to 5 picoseconds, and each lane 8-bit, that's 1 byte for each lane, and you can see its state at the moment of polling. And where you have a high-level signal, you have 1, where you have low, it's 0, but we found that this format is very unwieldy for real-life field investigations, so we had to write our own converters to convert these outputs into hexadecimal. Also, you can see moments where frequency disappears in certain lanes, for instance, in PCH, part of the blocks start getting disabled because of the energy-saving feature, and these moments are also marked here. But, as we said, the logical analyzer converts this data to its own private format and send it to get trace. But it turns out that trace engine has a special mode of operation, so that a very detailed log of this trace data can be built based on what you get from the logical analyzer. For instance, if you are not happy with the text format, you can take a look of this debug mode output in order to get more details about sophisticated cases. So this slide is a step-by-step instruction of what you need to do to run hardware tracing at modern Intel systems. The important moment here is in that, apart from these two files, NPK XML and visa.xml, that Visa supplies in the System Studio. It was supposed that they should exist for every platform. Well, actually, they appear and disappear in different Studio versions, but they are supposed to exist for each platform. But they're not enough. Apart from them, you need to have another file, which is interview.xml. In certain versions of System Studio, we found examples of such files, and actually the purpose of this interview.xml file is just to connect the signals coming from logical units into hardware events using some logical operations and signal values. And then these libraries, TraceHub API, they will operate with hardware events that they got from the interview XML file. But you'll have to write this file yourself. We've shown this its format. It's very simple. You take the complete path of the signal, and its value is merged with values of other signals. And now about SOCHAP. As I said, this system on chip hardware architecture performance. In actual fact, it's quite a useful component. Just like the logical analyzer, it's embedded, it's connected to the Visa network. But instead of digitizing signals, it just takes and based on the current values of the signals, apply certain rules to enhance or make lower the value. And so it just sends the counter values to TraceHub. It can also measure the duration of hardware events with a very high level of accuracy, up to hundreds of events. And so instead of analyzing the file how long the signal was up, for instance, in write enable, you can just use SOCHAP to count these events. Let me add, basically what we have is a classic thing that exists in oscilloscopes. You can work by some trigger, and if I remember, you can set this trigger. So additionally, as Mark said, we have counters. So as a result, Intel engineers have gone and implemented, a real high-speed logical analyzer on the chip in order to simplify the debugging on the one hand, but on the other hand, people developing hardware, and it may be about small companies or large companies, but not always people have equipment good enough, or let's say gigahertz class oscilloscopes to understand, okay, we've taken the board, laid out the board, and if the chip is good, but if you've done it yourselves, there'll be a lot of errors there because you don't have enough experience. So using this technology, you can at least see where the error is. Some signal is not arriving, or you're sending some signal at the wrong time, or if you want to diff it with external signals. For instance, when you're laying out some memory, such as DDR, it's actually quite difficult. You need to do the memory training, and it's a difficult operation, and you need to somehow debug it and find errors. So just to make this thing cheaper, Intel engineers decided to implement this kind of assessment as a logical analyzer on the chip. Actually, it's quite an exciting idea, I think. And we immediately get a question if this Visa technology has practical value for researchers. IT security, hardware, firmware, management engine, whether it has practical applicability, or maybe its value is limited by the area that it was intended in the first place. That's the validation of chip debugging. Well, it has a great value for researchers who wants to understand the internals of an Intel chip. Using this technology, we managed, if not completely, but at least to a considerable degree, to understand how Intel on-chip system fabric works. Why is it so important to understand its purpose? IOSF. This thing brings together all hardware components. They're connected among themselves using this IOSF technology. In the past, the PCI Express bus was used for this purpose. Some other proprietary mechanisms that were developed or that were applied to specific chips. But then Intel decided that a certain standard needs to be developed to get these parts interconnected. Firstly, so that it would be easier to integrate internal hardware logic between different versions, and also to be able to use and integrate third-party developments into the same chip. And they're using this standard, OCSF, for that. This specification actually has arrived from systems on chip or mobile platforms. Then it migrated to PCH, and in the newest CPUs, we have examples of CPUs based on it. As I've already said, in order to integrate third-party IP units and also to be able to support different versions of the. So this is the mission of IOSF. Why you need to understand its internal operations? I think it's a key not only to the understanding but also to a security audit of the entire platform. It's like a master key to all doors. Like Alexander told us yesterday that vendors made mistakes configuring SPI controllers, don't provide access to SPI regions, entailing bad results. But if all the regions have been set correctly, the device, the controller, wouldn't it be correct to suppose they should understand who is going to read it? So this way to provide for the integration of devices is very important. If you understand it, you're in a good position to offer some hypotheses, to look for bugs in certain places. You understand how it works. So using Visa, we sorted it out with this bus. And we understood the following thing. Each device within PCH, whether it's an SPI controller or a USB controller or some other multiple devices that are integrated there are dozens of those. So each of these devices has a unique attribute called security attribute of initiator, or SAI. So each transaction of each device is assigned with this attribute. And the other device that is a receiver for this transaction, it immediately identifies the one calling it. So basically, it's just a number. There's no encryption there. It's just a regular bus with address bus and data bus, and it has special signals that describe SAI. In order that information flows be separated, as we believe. Yes, and the specification itself, Intel system of the chip fabric, consists of 3 buses: IOSF primary sideband and debugging bus for FX or JTAG. We're not going to talk about FX today. It's just JTAG specification adapted for a hierarchy of devices. Whereas for, I say, primary sidebands, I'm going to talk right now. So the IOSF primary bus is intended. And by the way, we got a part of this information from Intel patents, but to take a look at it live, how it works in runtime, has only become possible using Visa. So I can say that it's been designed to control all the main data flows within the chip, within PCH, within the system on the chip, and modern CPUs. Actually, it's a broadened PCI Express specification, but it's very much adapted for energy efficiency. And it's based on a special device, special IP unit that's called a primary scalable fabric. It's like a foundation or the backbone of this bus. Actually, it's actually a router to which different devices are connected through different ports. But the most interesting thing is that the transaction, in terms of the PCI Express standard, the transaction is being routed either based on the address or BDF. So within IOSF Primary, the routing is done absolutely differently. For each transaction, its method of routing is set, the so-called destination ID, or DEST ID, as it's called in some data sheets or patterns. And it's also important that this destination ID determines a specific PSF where this transaction has to arrive at. It's a much more flexible way than than just address-based routing. I want to read this address and I don't know which device it belongs to. Whereas here, it is clearly indicated which device and which port this transaction should belong to. And also, this routing mode can be used to instruct the fabric to define the device itself. Also, what we found quite curious was that within PSF, there are settings, MTD, for each of the root spaces. A root space is basically some abstraction that where the device as such operates. So the device so this is done so that the management engine so the same device could present different interfaces to the management interface and to the CPU. So within each root space, this PSF unit allows enabling or disabling VTD. I think it's quite exciting. Yes, let me just add. I think a good example of how it works runs like this. So you have an SPI controller where you have your BIOS running. And the point is that when a CPU turns this SPI controller for some address, SPI controller says, okay, good. So I got the CPU coming to me. So I need to take the PCI controller and collect some data from a flash drive. Okay, good. But if CSME runs, one of the most curious things there is that modules there are compressed with the Huffman algorithm. It looks to be good, but Huffman tables are hardware implemented. You can't get them. So when an object comes up and says, address the controller, it says, okay, you're ME, you can go use those, or access those registers of mine that can support Huffman algorithm. So this is a good example of how root spaces allow separating the privileges. So who can access what depending on the functionality. So whether it's a CPU or PCH or something else. Maybe PMC controller or CH. So that's another way to distribute information flow so that you, for instance, wouldn't be able to ME code from the host without going to. So, okay, if there's a certain mechanism that allows initiating these internal transactions, these are internal PSI transaction. For the PCI bus, you have an adapter, a bridge to IOSF Primary. So if there's a way to work with these transactions, or even better, to fake SAIC. So I think this whole idea doesn't make sense. So our key idea is that if you find a device for which you can set the SAE, that's it. You're going to get access to such secrets that no GTAG will give you. But you need to know where to put stakes on. But it's not such a big problem, because SAE, repeating myself, is just a number. So running ahead, I'd like to mention that we've already found a way to learn SAE without going to a specific device, but we're not going to disclose it right now. It's a matter for our next research. And the second bus that, in terms of IOSF specification, exists is the sideband bus. It's not really needed for the mainstream data or communications. It's a service bus that allows setting up some closed configuration or get some closed information about the device that it protects, or maybe some error messages that are not supposed to come up very often. So it's a low-speed bus. But the most exciting information goes through this bus, IOSF sideband. For instance, gateway or platform gateway information. We've found out that there's a certain set of data called security fuses, which is key to the entire security system. It's like a root key for the entire cryptography of the management engine. If you get this key, then all technologies, all security technologies that are based on the management engine, such as bootguard or, for instance, identity protection, TPM, well, software-based, or DRM, all these technologies will certainly go down if you get this root key. And this key is being sent between the fuse control and a special device that management engine is interacting with over this sideband bus. We'll show you a demo video that will show how we can trace this sideband bus to get part of these keys. I mean, root keys that the management engine deals with. Also, I'd like to note that there's a special PCH device that's called DFX aggregator. It's a special device that manages all platform security. Basically, it controls what JTAG can do on this platform and what it can't. So whether you can debug the engine, or you want to get access to a certain device, it's all defined by DFX aggregator, and it also does its management using this sideband bus. I am sorry, we don't have a lot of time left till the next presentation. So that's basically how IOSF internals look, what IOSF internals look like, and if we can start a video. So it's about security fuse tracing. What we're doing here is we're setting up the signals that we want to take a look at. We're setting up in the beginning. Well, there are going to be two ways to read fuses through ME, not Intel-based but vendor-based, so-called, as they're called. We've basically reported about this at Confidence with our colleague Dmitry Sklarov. So there are two ways that we use to count the fuses. Firstly, we do it via Visa, and then we'll show you that they've coincided, that they match. So these are the fuses that we read via ME. As you can see, this is a coincidence. They match. Can we switch to the presentation back, please? A couple of words about the host. So don't have the time for more. So we took a look at the Intel System Studio. That's basically a platform that's responsible for it all. So we saw some binary files with understood that they're encrypted, and within the binaries that sit there to work with them, we found the decryption key. We decrypted all our files. In the same way, we started to look around and starting to understand if we have anything valuable in XML. And there are certain files where there are quite a lot of data for some period of time, and before it and after it, there's not a lot of data. So you take a closer look, you can find some interesting. For instance, we found some secret source. It's a description of fuses for the SoC. This, by the way, is about quantum. It's one of the obsolete systems. Also, we found the debugging mode that includes the deterministic mode for the random number generation. A couple of words about security. There are 3 or maybe 4 ways of deblocking. So, red lock for Intel engineers, orange for engineers and providers, such as ASUS. Green applies to platforms that you buy in stores. They're locked in some way. And also there's a white access level that perhaps only Visa needs. We've also discovered that it looks like there's a fuse that allows disabling Visa on production systems. But as you will see in the future or have seen in demos, these are not the platforms where it works. So how it can all be enabled? 2 ways. Firstly, via the vulnerability, you can get to GitHub, download the upgraded software that we posted quite recently, write it down on your platform, and from then on you can experiment, read logs, observe things. You'll have full access to Visa and a running platform. So bring itself up, operating systems will be launched, you can trace. Can I have a demo, please? So what we're going to do here. So we're going to trace addresses of physical memory. So on the right, we have read-write everything that reads values based by address. We stop Java, or we enable Visa. After that, we download the data to the computer. So this has happened. Basically, gigabytes have flown within several seconds between is just about the physical address tracing. So what we see from physical addresses is what goes. So within these 2 seconds, after we run it, so we see that we stopped and uploaded Visa. So we loaded here, and we're looking for the address we're seeking. So that's basically it. 77C5A6, exactly the same address that read-write everything reads. Can I switch back to the presentation? So we believe that it can be enabled through other vulnerabilities, and a couple of times a year we're getting more and more of them. You can write an exploit that activates it all. We've also found out there's quite a curious thing. If you have fuses that haven't been programmed, so programmed fuses is bad. Especially for mobile platforms, because this is where you can do it. You can sign your unlock token, and you can activate Orange Unlock. And then for some reason, Orange Unlock will throw JTAG ME at the mobile platform. So nothing like that on desktops and servers, but on mobile platforms, this is the way it works. We've talked with Intel about this, but Intel said it's a design feature. And we've also found a curious peculiarity that a special password is embedded in the bridges that allows you to do a hardware-based unlock to connect DCI adapter. So it looks, you can see it from the XML file. So how does it look? So you have some few stations in production that call for unique ID, unique password from the Intel server. Then it burns this value into a chip, and as soon as you need to debug something on the production platform, and I emphasize production, so a special traced person will connect an adapter to it or just a USB cable, will ask for some special closed Intel server, and this server will send it, authenticate them, and send them the password. After that, the password will be sent to the chip, and you have read and unlock. You'll be able to trace signals. You'll be able to gain access to internal CPU states, bridge states, whatever you want. We found a presentation where a former Intel engineer is writing exactly about how he uses this thing. He analyzed power consumption of the CPU. The presentation has been taken from GitHub after we published it there, removed the site, and everything has also been removed from the web archive. So once again, I'd like to say we didn't get this password out. It's hashed. Its hash is contained in the fuses, and it's unique. But we are basically confident it does run like that on the production platform. And basically you can try it with hardware. There's just one command that needs to be instructed. If you skip this transition, you'll also have a read and lock on the bridge. And that's basically it. So, the main thing, briefly, the main idea is that Visa is not really about vulnerability. Visa is more about research. You want to take a look at how it works under the hood, so you do it. And you just need to go and take a look. And you can do it on production platforms. Yes, indeed, there's a certain password. Visa allows you capturing them at a high clock frequency. You don't need taking samples, so you don't need to have very expensive equipment. So it looks like there must be a bit in the fuses that disables it on production platforms, but for understandable reasons they never install it because just in case. So unfortunately we've run out of time. So if you have any questions, I think we can take them offline.